now I have to build up a time switch where number of input slots and number of output slots per frame are different. So, this can be done using a dual memory system. So, let us see how this will be done. So, idea is that I will have a RAM kind of thing and or whatever switch, I will have M slots and outgoing I will be now requiring 2M minus 1 slots. But you can see there is a problem here, the clock for reading and writing from the memory has to be derived from the same source. So, its synchronization can be maintained. So, normally both of these I should be able to, both the clocks for reading and writing I should be able to derive from the same source. I can do that if I put it as 2M. So, normally 2M minus 1 kind of implementation will not be there, it will be M by 2M. So, there will be 2M minus 1 slots in the 125 microsecond frame and there will be M slots in 125 microsecond frame, and the clock will be derived from the input, and I will actually do the doubling thing, a doubler, but to create a double rate clock for reading operation. So, we will be using 2 RAMs here. So, let us build up the structure. So, we will have RAM 1, we will also have a RAM 2. Now, in the earlier switch, time switch, I was using only one speech RAM. The reason was that in first half of the clock I was writing, second half I was reading, or other way around also it can be done, but it was possible. But here the read is at double the rate, how you will do it in one clock period. So, the idea is that when you are writing in one RAM, you must be reading out from the second RAM at faster pace. Now, you will not be reading all the slots, remember, because number of inputs are only M slots out of these 2M will be occupied, not all of them, except in case if it is a multicast. If it is a point to point, one to one connection, then only M of these 2M will be occupied. So, other slots will go free. So, these will be tagged in control memory as a free slots, so that you can actually use them for routing the calls. Okay. But some garbage will at least will be read out even during that particular period. Okay. So, you will have a signal coming up and obviously you will be getting a serial TDM stream. Okay. So, you will be doing parallelization. So, I am assuming you get a parallel stream out and you have already got the frame clock from here. So, this is required to reset the counters as we had done earlier. There is a word clock recovery. And of course, you will be now using this word clock, and of course, you have to now toggle the first frame, this has to write, second frame this has to write, third frame this has you have to write here, fourth frame, and when you are writing here you must be reading here. So, alternate has to happen. So, I will take this frame clock and use a divide by 2. So, I can multiply as well as divide, both will be required. So, once I divide, this will be telling whether value is 0 then you will write here, when it is 1 you will write here, when it is 2 you will write here, when it is 3 you will write here, and so on. So, this particular clock will be used for toggling between the two two speech memories. Now, word clock, again I will generate two forms, one will be multiplied by 2 because we have to read out at faster rate, twice the rate. So, there is a multiplied by 2 multiplier, and I will use a counter which will generate the address. Okay. I am actually using here a write cyclic and read acyclic configuration. Okay. So, I will have a switch. So, this will decide, the value here will decide whether it will go up or down. So, this can become the input for this or this can become the input for this, and this value I call as A. So, when A is equal to 0 you will be writing in this RAM, A is equal to 1 you will be writing in this RAM. You will also be reading actually, remember. So when you are writing here you must be reading from the bottom one. So this should be A is equal to 1 and this should be A is equal to 0. So currently I think A must be 1, that is why this switch has been set there. Okay. So I will be also using this is the clock 1 input. So remember in one cycle, in one frame, this will be clocked with the this word clock, in the second one will be clocked with double the rate and then flip over. When the next frame will come, this will now be driven by this clock and this will be driven by this one. Okay. So we will actually do that. So this is the clock and this will also tell, this A will tell whether the read or write operation has to happen. Okay. So if you call it RW bar here, RW bar here, so when A is 1 you are writing here, so this will be fed by A bar, okay, and this will be fed by A, okay. So when A is 1 you are reading out from here and you are writing there. Now I also need to give the address, so I have address address 2 and I will have a mux which will have address 1 and address 2 as out. So counter will be coming all the way here. So this will be driven by A. And this one will go to control memory output. Okay. So for this switch I call it XXXX switch. So this will be cross bar state when A will be equal to 1, okay, because when A is 1 counter thing has to go here so that you can write down, while what has to be read out will be coming from address 2 which is going to come from control memory. Now this counter value actually you cannot pass on to this control memory, you require a different counter, okay. So this frame clock will be used to reset here. There is another counter which I will put. This counter will count for twice the number. If this will count from 1 to 8, this will count from 1 to 16, okay, this is double the size actually. And this counter is what I am going to use it. And this is the input which will be coming from the CPU which is acting as a control for this particular system, okay. And I can take this as an input to this, and now this one is also, because this switch is being derived by A, so this also will be controlled by A. So when A is 1 you are actually sending the reading here, so the writing has to come out. But remember there is also another problem, that not only A has to be there, but you also have to now ensure that you can write down into this, because this will be all the time operating. So one half this will be acting reading out, another half it will be you can write into this control memory. So in fact I should not connect A here, I will be actually using this double rate clock it will come here. So, in the one half when the clock is positive, double rate clock is positive, I will read out, second half I can write into this, but this is being triggered at double the rate and it is reading all the time. Okay. So, only thing the flip over will happen between this. So, the reading signal will be going to this or this will be decided by this particular mux, and they are being driven by now different clock. This is the frame clock divided by 2 and this is the word clock multiplied by 2. So, there is a difference here. So, this is a different than the earlier time switch in that sense. Okay, this I think gives the complete dual memory based time switch. Now, the problem is the number of times you are going to read out is twice. So, which locations will be read? So, normally whatever locations you are going to read, the 8 of them will be correct, remaining for example you can all set to 0. So, out of these slots which will be coming, these 2m slots, only m of them will contain the actual information. So, wherever the information is not there as per the map, it will contain information which is duplicated from one of the cells, so say 0, the first one. Okay. But normally what happens, that this will be kept track of by the CPU or the controller, which particular slots are being occupied, which are not occupied. Based on that, whatever path is or the mapping is decided about this particular switch, it will decide what has to be written in this control memory. Okay, before I move further, I had talked about time space time switch. So, normally the addressing there is very important, how the control memory actually operates. So, I am just going to take a very small example to show, and then we will talk about the various properties which are required. So, this is a time switch. So, it is M to M, then you have a space switch. Okay, so multiple of them and then multiple outputs is a time multiplex space switch, and I can have another time switch. Here you will contain 2m slots and here it will be m slots. Now, if you recall that when we are talking about WCRA and WARC kind of time switches, I have talked about the control memory of this. What I am going to write in the control memory, how I should do it, so it becomes much more cleaner system. So, normally if you want to have an scenario, you can actually try this thing out. You can take WCRA here, you can try, there is a control memory corresponding to each one of these outputs. Okay. So, you have to write something in that. So, in this case there will be 3 control memory corresponding to 1, 2 and 3. So, you want to, for example, this m is equal to 8. So, this will be 16. So, this will be 16, this will be 8 and this is 3 by 3. And you want to, for example, take one input number 1, slot number 6, you want to map it to output number 3, I will put a comma here. So, input number 1, slot 6 goes to output number 3, slot number 5. How this will be done? There are many ways. So, most important thing is this 6 slot has to be mapped to some slot here out of this 16. So, you can arbitrarily choose and map it to say 10. So, in the 10th slot, the cross point between this and this should be snapped, which will be governed by 3. So, in the 10th slot somewhere here, it has to write which particular point. So, it will be 1, 2 or 3rd which snaps. So, it will be saying the first cross point has to be snapped. So, this get connected to it in the 10th slot. So, in the 10th slot here you will get your stuff, your byte which is coming from here from the 6th slot. So, 6 to 10 it will be mapped by this. So, what you will be writing in the control memory here? Remember, it is a right cyclic and read acyclic. So, once it is right cyclic, 6th must have been written in the 6th location. So, in the 10th location you must be reading out, reading a, so 10th location you will be reading from the 6th. Okay. And of course, now you want to make it also right cyclic and read acyclic. We can try out all combinations. If I do this, what I need to write, because I am now mapping from the 10th slot to the 5th slot here, and it is right cyclic, so it must have been written in the 10th location here. So, in the 5th location, because I read acyclic, 5th location here, I need to write that I need to read out from 10. All control memories are working in a different fashion. Okay. So, here I am reading a 10th, here I am reading a 10th, here I am reading a 5th. But remember, if I actually use WARC, then this will get reversed. I will be now reading from the 10th location. So, let us do that. If I do this, I am now writing acyclically. So, I must be reading out from the 5th location. So, in the 10th location I should write in the 5th location. So, I will actually have the address 10 and I will decide on the 5th. Is wonderful actually. You see, every time slot is being whatever is happening in the time slot, that is governing the addresses in all the 3 control memories in all 3 stages. So, whatever is the input port comes here, whatever is the middle slot which I am using comes, whatever is the cross point will be used at the 10th slot, the middle slot will govern the memory location where the writing has to be done. It has become far more simpler to handle. If you do it other way around, if you want to do it in this fashion and you use it WARC here, then it becomes a mess, because at the 6th location you will be writing 10, at 10th location you will be writing 1, at 5th location you will be writing 10. Locations are not same. So, the main controller, it has to remember that at which location what has to be done for same connection. If I use this is what exactly is being done. If I use this, life is cool. For one particular connection all memory locations are same. So, I can use one single address bus for all addressing all the control memories simultaneously while writing into them. Okay. So, because all these control memories have to be communicated from the central controller, which will write words into this, which will cause a connection to be set up out of this through this digital switch. Okay, now let us look at the various properties of the switch. Generally, we would like to analyze all the switch properties, these particular properties in any switch configuration. So, these are very important. So, first and foremost is a strictly non-blocking system. And you will understand that all switches which are strictly non-blocking is a smaller set, okay, and all these switches, so I can keep on increasing my, basically I can include these switches. If I include more, I can have blocking and rearrangeably non-blocking and so on. So, let me define these, and then this set relationship also I will explain for all these combinations. Now, strictly non-blocking switch configuration means what? If I have a switch, strictly non-blocking property, if I have a switch, I have one free input port, I have one free output port, and I have inputs. So, these can be connected in any arbitrary way I wish. Okay. So, whatever be the connection pattern in this, if the free input port is there, free output port is there, and I can, without disturbing these connections, I can always set up a path between them, then the switch configuration is known as strictly non-blocking configuration. Okay. So, that is a kind of a definition in a understanding sense. We need a more formal definition. Why we need a more formal definition actually? Remember, in this case I have only talked about one input and one output. I have not included the case of multicasting. Multicasting means when from one input I can connect to multiple outputs. Okay. So, I need to include that. So, let us look at the formal definition. If T will be set of all transmitting terminals which are basically inputs of the switch, we have some T prime which is subset of T. So, which actually means this whole thing is T. I can actually have some small number thing which are T prime. So, T prime will be subset of this. This can be any set. Okay. So, I can write T prime is subset of T. Then you have R, receiving terminals or ports. This corresponds to the output side, and whatever is not being used, any subset of this will be R prime. Okay. So, R prime is a subset of R. Now, each element from T prime is connected to non-empty and disjoint, and I am talking about the set of output terminal. One element from T prime or one port connecting to multiple ports is possible. So, this takes care of the multicasting scenario. Disjoint subset of R prime, and we define a very important term, legitimate multicast tree. Okay. So, two inputs cannot merge into an output, that is important here. An input can only split into multiple outputs, and once it is connected to an output, no other input can get connected to that particular output. So, that is a one condition. Second is each element of R prime is connected to an element. It will be only connected to only one element, it cannot be multiple of them. An element of T prime. So, basically T prime is set of all input ports which are already connected. R prime is set of all output ports which are already connected. Now, T which belongs to T minus T prime, this is a free port, one free port which I identify as T. T belongs to T minus T prime, the subset which is subset of free ports. If T which belongs to T minus T prime can establish a legitimate multicast tree to any subset of r minus r prime. Important thing here, without changing previously established paths. And this should be true for all possible, in fact I should not write, I can write all t prime, r prime and all connection patterns between t prime and r prime. Then switch will be strictly non-blocking. So that is a very formal definition of a strictly non-blocking property, and this is in terms of the multicast tree. Now we also actually have other definitions. So second one is the rearrangeably non-blocking property. We will formally define these and prove that under what conditions a 3-stage closed network will become strictly non-blocking. We already know of that, but now we will formally prove it for a unicast scenario and then for a multicast scenario. Now the next property is rearrangeably non-blocking property. This will, formal definition remains as it is intact, except now this definition holds if t belongs to t minus t prime, okay. One can establish a legitimate multicast tree to any subset of r minus r prime, may require dismantling and re-establishing the previously established paths. And this should be true for all t prime, r prime and all connection patterns between t prime and r prime, okay. Then switch is rearrangeably non-blocking. Okay. Then switch will be rearrangeably non-blocking, that is a second category. So we call it rearrangeably non-blocking property. Now the third condition is, we call it wide sense non-blocking. So let me modify this same thing itself and we call it wide sense non-blocking. So again same definition t prime, r prime, t and r, and if I can want to set up, one can establish if T belongs to this, one can establish a legitimate multicast tree to any subset of R minus R prime, okay. And I will not be actually dismantling and re-establishing thing, I will not be disturbing any existing connection. And this can be done for all T prime, R prime, and I will now, this is an important thing, not all connection patterns between T prime and R prime are permitted. Now, important thing is that for example, if I look at a switch, a 4 by 4, I am just taking an example, I can set up 1, 2, 3 and 4 to 1, 2 for example 3 and some configuration like this kind of thing. This internally in the switch can be done in multiple ways, not in more than one possible ways. We call it a state of the switch. So, for this input to output map there can be multiple possible states and that is a connection pattern, okay. So, I will not be using all possible states, okay. If certain switch states avoided by suitable algorithm, so there has to be certain operation algorithm which have to be used. If it is suitable enough, then switch will be wide sense non blocking switch. Okay. And of course, the fourth category is the blocking switch, when there will be situations when input and output is free, whatever you can do you will not be able to set up the connection, this will be happening once in a while, then it is a blocking configuration, okay. So, fourth category is one cannot establish a legitimate multicast tree to any subset of R minus to at least some subset irrespective of rearrangements or operation algorithms then switch is blocking switch.